Good morning, everyone, and welcome to another Quanser Live webinar. In this webinar, we want to show you how to kickstart 2023 with a new QDrone 2. Find out what makes the QDrone 2 the ideal aerial research platform. My name is Michel Levy, and together with my colleague Gemma Wang, we will be your hosts and moderators this morning. Today's webinar will be presented by John Pineros. John has been part of Quanser's academic applications engineering team, which develops content for teaching on undergraduate control system concepts, as well as research examples for a studio offering. Over the last 5 years, John has been involved with training end users on how to set up and use the Quanser's Autonomous Vehicles Research Studio, as well as developing ROS examples and teaching content for our Quanser self-driving car studio.
Thank you very much, Mitch, for the introduction. Hello, everyone. I am John Pineros. I'm part of the academic applications team here at Quanser. And from wherever you are in the world, welcome to what makes the QDrone 2, the ideal aerial vehicles research platform. So before we start, in case you have not had an opportunity to know Quanser and its solutions, our name comes from question and answer. And my plan for this webinar is to answer the question of the QDrone, where we've come from, what our current offerings are, and with the QDrone 2, how you can jumpstart your aerial vehicles research. Now, if you've had the opportunity to be in a webinar with me in the past, you know that I like to start with a motivation, kind of look at what the current state of affairs is, what our current solutions offer, as a slow introduction into the content that we'll be covering today. The next portion will include an intro to the QDrone 2, where we will look at its comparisons to QDrone and what have been some of the updates. And then at the very end, we will open the floor for questions. So without further ado, let's start with the motivation. So when it comes to Quanser solutions, where have we been in the past? And what has been some of the solutions available for aerial robotics research? So we started our journey back in 1998 with the 3-Dove Hover. This was a multi-rotor platform that allowed researchers at the time to look into multi-rotor control. With extensive curriculum, it allowed users to get an idea of what it would mean like to not just look at fixed-wing aircraft in terms of the aerospace community, but start delving into multi-rotor control. We fast forward 8 years, where we are now looking at intelligent remote and sensing, where we start this idea of looking at unmanned systems and what it would mean like if we were to communicate with them. This one happens to be out in the field. And with that knowledge base, we start looking at flying quadcopters with the Cubot family of products. Extensively modified throughout the years, they have allowed us to give researchers the ability to look into multi-rotor control, now not just as a desktop solution, but actual combination of an aerial platform in your research system. We are also looking at the idea of cooperative control. As soon as you are able to control one aerial vehicle, a natural next step is how it would look like if they were to cooperate in space. That leads us into the release of the Multi-Vehicle Systems Lab and its various iterations. As you can see here, this started out with one of the first iterations of our ground platform, the Qbot 1, and its modifications throughout the years. And so we can see how the complexity of our systems start from a stationary testbed all the way to a full unmanned system solution, with also looking at the ground vehicle itself, haptic feedback as one of the other strong points of Quanser solutions. Now, with all the knowledge that we've gathered, in 2018, we released the QDrone as part of the AVRS solution. The intent at this point was to take all the knowledge we've gathered from the Q-ball and what made it a successful platform and truly give you a flying computer. With now onboard sensing in terms of cameras, you could truly take what was not just control for a multi-rotor system, but also look at expanding its applications in terms of you have multiple drones flying in space. What would that swarm control look like? What would that trajectory planning look like? And also collaborations with a ground vehicle. Now, after 2018, we asked the community what they would like to see. And it's the reason we're all here today, looking at the QDrone 2. But I won't show it to you just yet. It is silhouetted, and hopefully in the second part of the webinar, I can pique your interest into what are some of the amazing features that come with our platform. So our current vision of the Autonomous Vehicle Studio, as we can see here, and if you've had the opportunity to be part of our training, you know I usually start by pointing out what are the multiple aspects of our Autonomous Vehicle Studio. Any lab in general will use a motion capture system. Out of the box, we provide OptiTrack. If your system or your lab also uses Vicon, that is also a viable solution. We also look at the idea of a ground station system. Very common in aerospace applications for you to be able to monitor what your vehicle is doing from a safe space, which happens to be our control station. Now, in order to be able to communicate with our system, we also need some sort of network communication, which in our case is a Wi-Fi router that is provided with our solutions. What this allows you to have is a very contained and controlled environment where you can truly develop unmanned systems applications. Now, for the longest time, the platform that had the most variety was our ground vehicles, starting off with the QBot 1, being modified to QBot 2, 2E, and most recently the QBot 3. But starting today, if you currently have a QDrone, your aerial research platforms are now more diverse because of the inclusion of QDrone 2 and what this truly means in terms of making your research flexible. Now, when it comes to the actual workflow and how we were able to communicate with our QDrone and what made it really powerful was the idea of this ground station control, which I showed you a second ago. And using MATLAB and Simulink, we were able to rapidly prototype control algorithms that allowed the drone to stabilize in space. This communication was done via Wi-Fi, and once we had developed the controllers required to stabilize our system, we were using an embedded computer, which at the time was the Intel Aero, to truly actuate and get real-time sensor information back into our ground station so that we can monitor what the drone is doing. I have a generation of control signals allowed us to actuate the individual motors, and the drone was allowed to fly in space. And so we have this self-sustained computer that is doing real-time calculations at 1 kilohertz, and you as the operator can safely look and see where your algorithms may need updating, modifying, or if you're a student learning at how drones themselves can be positioned and control the space, have a safe way to do so. So what did that look like? So starting from the left, we can look at a training session that we had at Queen's University, where we have multiple drones running the same software, but it is the ground station that it allows us to define where the drones go in space. And so the outcome is this leader-follower scenario where they're maintaining this nice and safe distance. It is the same controller running on both. And so we can see very rapidly that the drone offers a very flexible platform where you really not just look at vehicle control, but also trajectory planning. Another aspect that we looked at was heterogeneous swarms. As I mentioned before, our autonomous vehicle studio also offers a ground vehicle. And so back at Quanser HQ, we could also look at the very standard example of a leader and a follower. This no longer needs to be a QBot. This could be any ground vehicle that you have purchased from us. And as long as they're part of this unmanned system solution, you can also look into research with swarms. But as we can see here, there was a lot of collaboration. It's not just an aerial platform and it's not just a ground system. But as technology has advanced, we want to be able to give you the best in terms of aerial research. And so I'm proud to pronounce the introduction of QDrone 2. Here it is. Taking a page from Nvidia and our lead scientist, I truly believe it is the world's smallest flying AI supercomputer. And I hope by the end of this webinar, I can give you an idea and give you an inspiration of what type of research you can do with our systems. Now, you can see that the design philosophy is very similar to the QDrone 1 in the sense of how we've protected our systems, but we've added more. QDrone 2 is not just a small step, but I believe it's truly an evolution in our aerial systems platform. So one thing that we can check, size comparisons, because we wanted to give you sensors and we wanted to give you the ability to create really intelligent mobile robotics applications, we had to get bigger. So as you can see on the left-hand side, the standard footprint of the QDrone with the QDrone 2 on the right-hand side. We can see that our PCBs got larger in order to accommodate the large number of sensors that we have available. This is now roughly a half a meter drone, diagonal measurements, but this truly allows you to take advantage of all the sensors that we have available. And in terms of the actual sensor suite that has been improved, here's a quick look. Taken from our product information sheet, we can see, looking at the left-hand side, the impact resistance. We've had a lot of communication with our community in terms of how we can improve our system, and we've made modifications. And so that's kind of the first step of we're looking at, where we're still sticking with carbon fiber to protect all the core components, but we're now expanding onto this. Now, the next big step is the actual compute unit itself. Originally starting out with an Intel Aero, it met the needs that we were looking for at the time, but leveraging technologies from our Q car to make it a very seamless interface, we've updated to an Nvidia Jetson Xavier. This allows us to not just do rapid control applications, but leverage machine learning at the same time. I will take a look at a quick example of that later on in this webinar. Likewise, we have improved our camera system, updating from the RealSense R200 present on the QDrone 1 to the D435. Likewise, if you've had the opportunity to use your Q card, you'll be right at home with the system. But not just this, we've also given the drone 360-degree field of view. And we will see an example of that later on in this video. As with any of our solutions, we also give you expandable I/O in case your research needs require more sensors than what we currently offer. Likewise, we also wanted to augment the downward-facing suite of sensors. With the QDrone 1, we gave you an Omnivision global shutter camera, and we've upgraded it for the QDrone 2. We've also given you a official time of flight sensor. So this allows you to get even more state information in case the areas of research that you're interested in require more information about your environment. Likewise, we have also included an optical flow sensor. So what we can see here is a very sensor-rich system as the QDrone 2 design philosophy. Now, looking at the actual core components on the inside, we've not just increased cameras, but we've also added IMUs. Again, looking at the idea of state estimation, having more information about your system and where it is in space is very important. We've also decided to take a step back and try to make the drone more modular. So we've actually dedicated an M.2 Wi-Fi slot, which allows you to communicate to the ground station via Wi-Fi, but also allows you to connect Bluetooth peripherals. So it truly gives you more flexibility of the type of information and peripherals you would like to attach to your system. As mentioned before, there are CSI cameras. They're located at the bottom, as you can see here, or on either side of the drone and one facing back. Now, we've also improved the power management system on our drone to make it something akin to what you would find on the Q car, as a way to make the system more reliable and more flexible. We can see on the right-hand side, if you were the user and were to interact with the drone, this is what you'd be looking at in terms of understanding how everything has been encased in a very highly protective shell, but also with the flexibility of you being able to add more I/O where you see fit. Now, we've talked about updating hardware and all the changes that have been made. And this is just a few of the changes that have been done. Under the hood, you still have more sensor information available for you. We've also increased the actual software platforms. So on the left-hand side, we can see that we, on our QDrone 1, currently have all our examples released in MATLAB and Simulink, which has been great as an application for you to develop rapid and safe control algorithms, but we wanted to expand. And by leveraging NVIDIA technology, not only do we get access to MATLAB and Simulink, but we also get access to the ROS community. If your research needs are more robotic centric, where you will take our out of the box examples and augment them or interface them in your system, the QDrone 2 officially supports ROS and ROS 2. With the addition of this, we have Python and TensorRT. TensorRT, being NVIDIA's implementation of TensorFlow, gives you full access to the TensorFlow library and the CUDA cores available on the QDrone. And we will see an example that uses the TensorRT library on the QDrone. So as you can see, it's not just an increase of hardware, it is also an increase of software, which makes this a very flexible solution. And so what could that mean in terms of your applications? We took a step back before where we looked at how the current applications are designed for QDrone 1, and we've expanded. So imagine you have a research team where one portion of your students is really looking at drone control. They can still utilize MATLAB and Simulink to develop the control applications that are stable, that require that fast real-time control, but also have a secondary team that develops applications that are maybe native in Python. and require the use of Ubuntu as the user interface. In this case, you can see that the QDrone becomes extremely flexible in how it is utilized in your lab, and you could collaborate across universities depending on department needs, or if you would like your students to get more hands-on in terms of what makes a current robotics platform. And so what does that mean in terms of applications? So looking at the left-hand side, we can see the standard position control that we have developed on our drone. And you can also take a sneak peek at the roadways available for our Q car. But primarily, you can see this is what the studio um, ethos looks like, where you have a motion capture system giving us state information of the drone. It is now controlling its position in space. And so if you had used the QDrone as the platform, this would be right at home in terms of the out-of-the-box examples that we currently offer. But now for something a little bit more fun. This is internal in our Quanser HQ, where we're actually testing all the cameras available on the drone. And I really like this video because it helps emphasize what cameras can do for you. You can see starting at the top center image, that is the RealSense view. The three that you see in the center are the left, back, and right side cameras on the QDrone. And what you can see is a complete world view. So imagine you're doing a state estimation or a mapping application that requires you to find key objects in space. This hopefully gives you an ability to understand that this is true world view of where the drone is in space, and you're not just confined to a single view being the front of the drone. But this has all been done using our Simulink access and our Simulink software stack. So what if we wanted to do something a little bit more interesting? By leveraging NVIDIA technology, we also have access to the Jetson Inference Library, which is a set of neural networks available by NVIDIA that you can run on any NVIDIA device. And so that looks more something akin to this, where we are running the standard position control example. But as you can see, an overlay of the actual Ubuntu interface, where our video feed is currently being classified and we're detecting key objects in space. The actual terminal window is letting you know information about what the neural network has found in space, the confidence in what it's seen, and some information about where that object is in space. And it'll do multi-object detection and actually let you know if there are multiple things present in the scene. Here's what you can do with them. And so you can see here in the back area of our system, here at Quanser, I'm using the neural network to figure out a backpack in space. It'd be looking at then the monitor on one side and then going back to a keyboard. But the idea primarily here is for you to be able to see that there is a Python application utilizing the TensorRT library and the CUDA cores in order to do rapid machine learning while at the same time having stable control for your drone. So you don't have to worry about the drone going unstable, and you can also monitor the CPU and GPU process times. If that is another area of interest where you would like to develop your own machine learning libraries or applications using CUDA cores and would like to see their performance, all of this is currently present available for you. And so in summary, we can see that the QDrone 2 offers the same level of Simulink support as what we had before, all of the same examples that you had and were accustomed to in terms of manual flight to get familiar with the drone performance, autonomous position control to let the drone go anywhere in space. You can still utilize the swarm and leader and follower because that technology is still the same. The idea of you either having multiple QDrone 2s flying in space, or maybe a QDrone 1 and a QDrone 2 as the aerial platforms, or expanding knowledge base in terms of having two drones in space, one being the leader, one being the follower, or the inclusion of a ground vehicle. We have officially introducing Python 3 support, and you saw what that looked like a second ago by interfacing with the Intel RealSense and the CUDA libraries. We're currently developing ROS 1 and ROS 2 nodes, so that'll be exciting. So please stay tuned to see what that ends up looking like when the product is officially released. So with that, I would like to thank you for joining me in this webinar, and I will open now the floor for questions.
Thanks for the amazing presentation, John. That was very informative. And like you said, I think we can proceed to answer some questions that came in from the audience. We have one from Lorena regarding the flight time and the payload of the new QDrone 2.
Okay, so the flight time for drone 2 is about 8.5 minutes. And in terms of payload, we're targeting the same payload that was available for QDrone 1, which is about 300 grams.
Okay, and what about the distributions for ROS installed on QDrone 2? This is from
Okay.
Patrick.
So, as mentioned, the QDrone comes with ROS 1 and ROS 2. The ROS 1 distribution is melodic, and the ROS 2 distribution is eloquent, which is the latest distribution of ROS supported by Ubuntu 18.04.
Okay, and from Anant, he is asking what kind of onboard image processing capabilities are possible with the addition of the new NVIDIA platform that we have.
So great question. There are a lot of image processing pipelines that you can go to. You could utilize something like OpenCV and take advantage of the standard set of libraries they have available. This can be anything from color thresholding to line detection. Or if you would like to go more on the machine learning side, that is the Jetson Inference Library. And so out of the box, you can get something that has object detection, which is what I showed you. You can also do a depth estimation using a neural net that they have available. There's another cool technology that is called PostNet, which if the drone is monitoring, let's say, an object moving in space, it'll actually give you an estimate of the orientation of those objects in space. And so those are all tools that are available that are directly using the CUDA cores for very fast computation.
Great, thanks for that. Yeah, one more question is can the QDrone and the QDrone 2 be used in the same lab?
For sure. So if you have the current QDrone 1, your method of communicating with it is via Wi-Fi, and the development environment is MATLAB and Simulink. So as long as you know the network address of QDrone 2, and let's say you are also developing an application in MATLAB and Simulink, they can communicate with each other. The QDrone 2 is not just restricted to MATLAB and Simulink. We have Python examples that allow you to initiate a stream communication. So if the QDrone 1 is sending key information to another agent in space, and that happens to be the QDrone 2, you can use a Python application to read that information and make some sort of high-level decisions that impact the way that the drone is flying in space.
Okay. Well, thank you. I think that's about it. There's no more. Yeah, I think that's all the questions we've had today. So yeah, this brings us to the end of our webinar. We'd like to thank everybody who attended today. Please visit our website, www.quanser.com, and our LinkedIn page to find out more about our systems and upcoming webinars. And have a great day, everybody.
Sorry, Mitch. I think we have two more questions in chat.
Oh, yes, from Kelly, if there's any demos for using both the QDrone 1 and the QDrone 2.
We're currently in the process of developing those demos. Um, from the architecture side, if you were to use the swarm example that we currently have available, that is broadcasting information to an object in space or an agent in space. So we could take the standard position control example that we have and connect that to the mission server used for swarm. And so that defines the location of the objects in space. So the example we saw with Queen's University, where they had a drone 1 and a drone 2, or sorry, two QDrone 1s, we can change that and have the QDrone 2 be the one closer to the center of the flight space and the other QDrone being further away. So the swappability and the flexibility of that is very open architecture for you to be able to design. Yeah.
Okay, thank you. And we had one questions from Amit at EduTech, but I think Murtaza pretty much answered it. But maybe if you want to elaborate a bit, this I'm sure will come up is can the QDrone 2 be used with the old QBots?
Yes, yes, it can. Just like with Kelly's question regarding the QDrone and QDrone 1, this is all communication via Wi-Fi. And so the QDrone 2 will support older QBots. That can be, you can include the QDrone in your previous flight space. That is definitely a possibility.
Great. Well, thanks a lot again for the great presentation, answering all the questions, and thank you everybody for joining us. And yeah, check out your inbox and we'll send you a link to the recording. So have a great day.
Thank you, everyone. Bye-bye.